Hey, can you guys hear me? You guys should be able to hear me, I think. And we should be recording. We are recording. So we'll make sure people can hear me first, and then we'll be good to go. Maybe I don't have my audio up. Audio is on for me now. Theo, can you hear me?
Yeah.
Cool. Okay, we're recording this time. So that's that's a pro. That is a good thing. And then we'll start screen sharing here. Let me get a new RStudio document open right now. So we're just going to open up some new stuff right here. Got like, geez, I always close down everything I have in R, and then I like everything gets just expanded upon all the time. So let's go ahead and start screen sharing. I've got a burger in the oven right now, so I'll probably turn off the camera in a little bit and like eat a burger while we're doing this because I just got back from office hours. So let's start screen sharing. And here, let's go to 1 second. We'll start screen sharing 1 second here. And we'll do all the questions. Okay. Start screen sharing. I'm going to check my oven every once in a while, so maybe I'll turn off my camera. Okay, we should have the desktop screen sharing. And then we can go over here to RStudio, and you guys can see everything that's going on. And let me turn off the camera because I might run around real quick every once in a while. So let me stop video. You guys can still see the screen, right?
Yep.
And you guys can see RStudio now, right?
I can.
Awesome. Okay. So we'll get started here in 1 second. I'm just going to make sure I don't burn down my apartment. It's always a plus. Okay. Okay. You know what I'm going to do? Okay. I got the toaster oven on a 5-minute timer in the background here. So, okay. Let's get started here. We can go through the topics one by one and kind of review what we've done, because starting out, we kind of just need to, I'm not clicked on the screen. We need to make a linear model right here. And maybe this will help a little bit with the take home too for those watching. You know, just making a linear model, we can do height, tilde weight. I already have survey 11 loaded in, I believe. I always use survey 10, so that's the one I got loaded in. So we just have a linear model here, and I misspelled weight, and it doesn't like that. My gosh, one of those days. There we go. Now we have weight spelled correctly. First thing we usually want to do is take a summary of it, and we can see here the coefficient of weight, the uncertainty in the coefficient, the ratio, and this is kind of nice because if you look at it, it's about 20 times bigger. Just kind of lightly breezing through some stuff. Please ask questions if you have it. This is mainly a review from the first test. We don't really go in depth on first test stuff, but you should still kind of know it because it's, you know, we use it in the second half. So we've just got a simple model right here. And we can do check regression on it. It never hurts to take a look at what's going on. It doesn't like my figure margins, so let's fix that a little bit. And we do have some outliers here for the model. We have a little bit of non-normality in the residuals. The linear looks to be all right, and we do see problems throughout this model. Looking at the p-values, kind of bad, and the graphics, it's not the best of models. But let's go to a new command here for this chapter, and we have the, let's do first extrapolation check. Extrapolation check is one we haven't seen in a long time, so I'm bringing it up. And I'm going to bring it up for a reason right here. It should give me the extrapolation check. It doesn't like that right there. And let's do survey 10. It's going to like that. It's not liking the parse on the new data. What is it not liking for extrapolation check? Should allow me to extrapolation check the data. And what is it not liking today, guys? Let me try one thing right here. Data frame, we are putting into this weight. So I'm just going to give it weight as a data frame and data frame weight equals, and I'm not going to put in multiple values, but we're going to put something really low in here. And that just made a data frame of weight. And so you just see here, this is now a data frame of one person who weighs 30 pounds. And what we should be able to put in here is the DF, and let's do extrapolation check, new data equals DF. And what is it getting mad about here? Incorrect number of subscripts in matrix. My brain is completely breaking today, guys. me try. What happens today? Extrapolation check is not working. How you guys doing today? There's silence.
I'm great, Brian. How you doing?
Awesome. Don't you love it when something just explodes like this?
No, not really.
I don't like it either. Let's see what happened here. Okay, so we need to load the salary data set. Okay. And now it's running there. And what usually I can get this to do, there, it ran right here. And this is what I wanted it to do. If you just run it, is it seriously not running because I just have one variable? Is that the way Petri coded it in? Let me add into this GPA. And let me try running my extrapolation check now. And it runs. Okay, so extrapolation check is coded for multivariate. And so if you notice, the only difference between my command now and what it was, I could actually check this person right here if I wanted. I give them a GPA of 2. And now I can do this right here, which I think will work as the second command, is their percentile. So we've got everything working right now. Extrapolation check only works for multivariate, which is insane to me. I would have thought it worked with just one variable, but it doesn't. So we actually went into the world of multiple regression, but Petri had it coded in, so it had to take more than 2, which actually kind of makes sense because you could actually check to see if something is an outlier in weight by simply making a histogram of weight and checking its percentile. So you could just went here to survey 10 and looked at weight to see if we're extrapolating on weight. So does that make sense how we would extrapolate on one variable? Like if we go back to the univariate sense here, you could talk about extrapolating outside the model by looking at the summary or the histogram to see if you would be extrapolating. Does that make sense right there? Like we'd be extrapolating outside this model, outside of 75 and 305, just for weight on the univariate. Does that make sense? Maybe?
Yeah, I'm good on that.
Okay, good. So in the univariate sense, this command is kind of superfluous. So the way Petri coded it in is when we do the extrapolation check, we actually need some multivariate. We need 2 x's or more. So now I've created a model with more than 1 x. And now when I run the extrapolation check on the model, I can actually find which one of these is the most extreme for extrapolation. And there's an easier way to do this. If I just look at this third column right here, these are the observations right here. You notice right here, this is the observation and the percentile. So I could just pull the percentile here, and of course nothing likes me today. Oh, because it's, there we go. Rows, comma, columns. What is wrong with my brain today, guys? Let me see this again. It's running, and let's do this. Let's just save this as E. Now that I've got E, oh, E only has 2. Petri, you make my head hurt sometimes. Okay, that works. These are all the extrapolation numbers, and look, there's 100 right here. This is the most extreme observation. It is the furthest away from the mean of all the values. Anything near 0 is actually very average. So we could count here 84, 85, 86, 87, 88. And let's go ahead, and I want to see something real quick. If we go to survey, and let's go inside of here, and I said 588, right? So this is row 588, and I want to see what this person had for values. We're using weight and GPA. This is a male who's 153 pounds with a 3.1 GPA. That's about as average as you can get, it seems, for weight and GPA. But then if we go to the 100th percentile here, which is going to be 61, 60. Does everyone see how I'm doing that right here with the rows? So this is the 60, and this is this 560 right there. That's 561. And if we view this person, we see here that this person weighs 95 pounds and has a and I want to point this out. This is the most extreme combination of weight and GPA. They might not be the lowest weight, but they are, I would assume, the lowest GPA. And we could actually look at our weight histogram here to see there actually are people who have lower weights. They're not the lowest weight, but their combination of weight and GPA is the most unusual. And to look at the bivariate, we really have to come up with some metric. And this was when we looked at the cloud. So the extrapolation check right here is seeing how unusual something is in their x's. And we could, of course, use new data right here if I give this person a GPA of 0 now, and I do the extrapolation check on my new data, this should be the 100th percentile also. And does that make sense why this is the 100th percentile? I could even re-simulate that other person, which I think they're on the 100th. Yeah, they were the most extreme. But if I bring them in a little bit, they won't be the most extreme anymore. And so I brought them in. If you notice how I went from, this is outside of all the data, this is the most extreme data point, this person here, and now this person's in a little bit closer. If I bring them more towards the mean here, we'll start to see them more towards the mean here. Does it make sense how this is working? And it's allowing us to maybe look at a new point and see if we have a new person here, like Brian weighs 190 pounds, had a GPA of 3.2, and we could see where's Brian at. I'm 50% away from the mean of both of these. I'm about 50%, I'm 46%. So it wouldn't be too big of an extrapolation to use the model for me, which means we can trust the model. And that's the idea of checking the extrapolation. Because if you're gonna make predictions, you want your model to be around that data point. Does that make sense on extrapolation? Sorry for the rocky start right there, but does that make sense?
Yeah, I'm good.
It makes sense.
Awesome, because then we're gonna switch over to influence plots. And you know what we're gonna see? If you remember, we have some points down here, and actually these crazy points over here are the ones that are extreme in the x's, and this is so interesting to me, because these ones that are extreme in the x values actually don't come back as influential. These are the high leverage points. I'm guessing this point right here is actually 560, because they're very extreme in their values of x's. But to have influence, you also need large leverage, which is extreme in your x's, but you also have to have a large what?
Why?
Kind of y, kind of your deleted residual, which means the model misses you. So the model needs to miss you by a good amount. Does that make sense? Like, visually speaking, I want to point out what this looks like in the univariate sense. I'm going to make this back to a univariate model here. In the univariate sense, for the model to miss you, looks like, oh, so I still have that other model in the background. Cool. Okay. In the univariate sense, let me make this graphic look nicer. Okay. Cool. In the univariate sense, leverage would be being over here or being over here. And it looks like the mean is about 3.1. We figured that out previously. The mean is about here. So these have extreme leverage. And that's why these came up with extrapolation. Because if you're extreme in your x's, then you're far away from the mean, which the model is almost extrapolating to predict you. And so being far out on the x is leverage. But this point right here is probably not that influential. And this might be our person who is very light, because the model doesn't miss them by much. And since the model doesn't miss them by much, they don't have a large what? There's pretty much two answers you could get for this. If the model doesn't miss them by much, they don't have a large what?
Leverage?
Yeah, that's what I was going to say.
You know, remember, if they're far away in the x values, that's leverage. So like these points over here have a large leverage. But as I go towards the red line, the points don't have a very big what. As I go towards the red line, the points don't have a big what. Like all of these are equal in leverage. They all have equal leverage, but they have different whats.
Influence?
That is true. That is true. And I'll bring up the two graphics. I didn't know it changed graphics if we did that. They have different, and maybe we'll show it. They have different influence because they have a different deleted residual. And that's kind of what you're seeing in here. This is our most extreme. I'm guessing that these are most of the points with GPAs of 0 because that's a very big thing. But then this person had a crazy weight. This is the bivariate leverage. It's hard to think about leverage when you have two variables, but it's being extreme in your weight and being extreme in your GPA. And we found that that person, we could go back here and view the data hopefully, this person here had a weight of 95, which is very extreme in their weight, and they have a GPA of 0. So that GPA of 0, and we're predicting their height, and you see how the model apparently gets them right? I'm gonna prove that this is this person. I'm gonna change their height to like 30, and I just wanna prove that we're actually looking at this person. So what I need to do now is I need to go to the vector of height inside of here, and I just want to prove this once and for all. We're actually looking at that this big dot over here is this person that we keep talking about. And I'm going to go here to the 560th. I'm going to change their height to be like 40, which makes them way down here. The model will now overpredict them. Does that make sense? So this dot is going to drop to here, and I'm changing it so that the model misses them more. So what will I be increasing? This is a good review here. I'll be increasing what by making the model miss them more?
The residuals.
The deleted residual, which if I increase the residual, they get more what? By increasing the residual, they will now have more what in the model? They'll have more influence. So by increasing the residual, they have more influence, which is the size of these circles. So now you should see, if everything works properly, this dot should drop down a good bit, and it does. That's exactly what I wanted to happen. Because I could identify this point. I want to make it clear how I'm able to read and understand this graphic, because the more leverage something has, the more extreme it is in its x values. That's why I started off with the extrapolation check, and I checked this person right here who had a weight of 95 and a GPA of 0, and it told me they are the most extreme in their x values. If I did an extrapolation check on anything in here, what would I probably get back for the extrapolation check value for down here, for a point inside of here?
Something close to 0, I guess.
Exactly. It'd be close to 0 because they're not extreme in their x values, which is the idea of leverage. But this was the most extreme. So I identified it, I knew who it was, and then I changed their value of y, which made the model predict them worse. And that's what I did down here, was I changed the value of y for that one individual. I overwrote the height of the 560th person and made their height 40, as that set the model just completely wrecked on it. The model couldn't predict them well, and now they have an extreme, they are extremely influential, denoted by the size of the circle. Influence is a combination of leverage, how odd you are in your x's, like are you an odd combination of height and GPA, weight and GPA for this model. And then the studentized residual, the lead studentized residual, is how much does the model miss you by? Are there any questions about extrapolation or influence plots? Like I kind of wanted to do a few examples and cover this right here.
I'm good.
Cool. And I mean, this is how I generally write the test. If you're thinking about how does Brian write the test, I create some models like this, and I look through them and I experience them, and I'm like, okay, how would I know this is the person who was the one where the extrapolation within the model was the most extreme? And we're talking about, because extrapolation is always a matter of extremes. Are we extrapolating outside the model, or what are we doing? And in this instance, this person is at the top end of the model, the very, very top end of the model. So that's got that. Let's go to another topic here. So we have multiple regression now, and we've got a multiple regression model, but we need to look at the choose order command. So if you remember back when we did the choose order command, go ahead and type choose order there. We need to start with just, and let's bring this here. And I'll probably upload this after too, so we can see it all. Let's go to choose model and go to GPA. So now we're going to see with the choose order GPA, and let's run it here. So let's make our model, and we're going to see if GPA needs to have any sort of higher order polynomial with it. And so I'll let you guys look over this for 1 second and tell me the right answer. I'll be right back. I'm going to grab my burger. Okay, which one did you guys choose?
Model 2.
I think maybe it's the 0.005. Okay, so we need to find the highest, right? I think it's model 3. This is an iffy one. So we need to find the model with the highest R squared adjusted, right? And that is model number 3. And then we go to model 3. I think it's model 3. And then we subtract 0.005 off of it, and it would be model 3. Does that make sense? I'm just making sure I'm reading it correctly. You go to the R squared adjusted, that's the highest, then you take off 0.005. And it's interesting to me also because we weren't using AIC at this point. This is the one with the lowest AIC. I understand it's probably a toss-up between model 2 and 3. If someone wrote to me and they said, I picked model 3 because it had the, like I usually like asking, why did you pick this? Because I don't want you guys to just guess. I mean, it's a 1 in 6 chance if you just guess. And you probably wouldn't guess like, you'd be like, okay, I guess it's a harder one to guess because you have to know our heuristic. But someone could maybe justify model 2. Why? What would you have to take me to justify model 2? How would you justify that one?
Because it's less than 0.039.
Model 2 is within 2 of the lowest AIC.
Oh, okay, very nice. I see.
Yep.
Yeah, I see that too now.
And these are key things to look for. I'm gonna try not to eat too much on stream.
So,
But
I have a question. Since we chose we took the highest the R squared adjusted of them, which was 3, and then we subtract 0.005, so which equaled 0.039. So why do we still include model 3?
one second. Well, model 3 has the highest R squared adjusted. I'm not eating anymore. Sorry, I usually eat lunch right when I come back, and I was starving when I got back. Model 3 has the highest R squared adjusted. Agreed?
Yes, sir.
Oh yeah, help me, sir. We have the heuristic we learned earlier on that we then take the highest R squared adjusted and we subtract off 0.005. And the reason we do that is we are possibly going to consider simpler models. Like model 3 is the model that is the best. Like, and you could say that for 2 reasons. It has the lowest AIC and it has the highest R squared adjusted. That is 2 major things going for that model. What is the only thing better about model 2?
It's simpler.
It's simpler. And you can justify, like if this was, and remember, when we leave this class, we have lots of tools we can use. If someone said, I want to use model 2, they could say the AIC for model 2 is within 2, and that's just, 2 is our heuristic for that, of the AIC of model 3. These models are virtually identical. Model 2 is simpler, the order of the polynomial. Does that make sense?
Yeah, it makes sense.
Yep. And what we would need to do now, we'd need to actually check weight. So I'm going to take one more bite. You guys, ooh, this one's a fun one. You guys tell me which one you'd use here and why. So think about that for the moment. Do like little pauses here. Like, which one would you use and why? Those are great questions on the test. Like, which one will you use and why? This is insane. I can't believe this one.
Is it number 6?
Yeah, it is, isn't it? I would go with the original heuristic we used because you should take the R squared adjusted and do what to it?
Subtract 0.005.
And then are there any within that range? Did I mess it up? No, it's not number 6. See, that's why you just make sure you follow your math. So the answer is actually what?
3?
Model number 4.
Oh, 4.
Because this is what you have to make sure that you still meet this right here. So we can go as low as 0.4205. And that's why you always just double check your math, because my eyes were blurring on that a little bit. It's so easy to make mathematical errors. And that's why you just type it in, you take your number and you say, okay, I'm going to take the highest one, which is easy to check for. And you subtract off. So you take the highest and then you subtract off the 0.005. Make sure it's 0.005, not 0.05. And then we can go as low as that. So could we use this one, yes or no? Could we use it? Not are we going to use it? Could we use it?
Yeah, you could.
Could we use this one? It's within 0.005, so we can use it. Can we use this one? Does it meet this standard right here?
No, I don't think so. Does it?
It does not. It's not. It needs to be above that. You want it to be above that to meet the standard. And you know what's funny? Take a look at the AIC of the model we just chose. It's the what?
The lowest.
It's the lowest. And then why wouldn't we just, this one's within 2. Why don't we use this one? Because this is within 2 of this. Why don't we use the 6?
Because aren't we going for the simpler model?
We go, yeah. You wouldn't go up to, you wouldn't say, well, that's within 2, I can use it. You wouldn't use a more complex model if it's within 2. You want to use a simple model if it's within 2. And then you look at all of these up here. I'm just saying, like, it's interesting to me that both ways we're doing this actually converge on the same answer. Like Dr. Petrie's 0.005 heuristic works with the AIC of 2. Like the lowest AIC of this is this model. And this model is actually the one we would pick by using the R-squared adjusted within 0.005 of the highest, excuse me. AIC lowest, R-squared adjusted highest, because it's R-squared with the penalty term. So does that make sense how to read this output right here?
Yeah, it makes sense now.
Cool. Yeah, it's just understand what the output's telling you, and you can kind of see it. Just looking at this graphic alone, I could have told you that we're gonna need maybe the 4th, 5th, 6th order, because you can see that the lines are all kind of bunched up. The previous graphic had them all kind of tight, so there's not many differences. But this one was actually making some differences, which I think is so cool because you can see the 2nd and 3rd are very close within their R-squared adjusted, and then the 4th, 5th, and 6th are very close within their R-squared adjusteds, and the linear model does its own thing. So that's got that. We then started to include in some categorical variables. So let's go ahead and make a categorical variable model here, and let's go ahead and head in gender here. Let's try to do some interpretations here. Now we got to watch out because our interpretations are going to flip, and interpretations are going to be very important for tomorrow. So I want you guys to interpret the coefficient of gender male in this model. And I want one of you guys to try that out here. I'm going to take another bite here. But go ahead and try to interpret the coefficient of gender male in this model. Silence. If you're watching this video, pause at these times and try to do it yourself. But I'm about to do it in 1 second here, but try to do it yourself. Because if you can do it, you're doing it. Okay, so gender male is an indicator variable created from the categorical variable gender. This is not me interpreting it, I'm just telling you what it is. Because if you notice I put gender here, this is where a lot of people are running into the problem that they'd say, there's no smoking now variable. Well, there's no smoking now variable because smoking now is the indicator created from smoking. There's smoking now and smoking never. And if you want to create the indicator variable smoking now, you would include smoking, and then the reference level would be smoking never. The reference level here is gender female. Gender female is the reference level. So we don't see gender female. An important thing, especially for the take home, this right here is the difference between gender male and gender female. Gender female does not have a value of this. It is true that that is the intercept, but gender female causes no change to the intercept. So gender female doesn't have a value of the intercept. It's just that gender female does not change the intercept. And we can see this visually here. The intercept for gender female is going to be right here. And then the intercept for gender male is 5.01 higher. So all of these estimates, the estimates and the standard errors, like this is the standard error for how much we think that the estimate differs from gender female. It's our uncertainty in how much gender male differs from gender female for this estimate we've created. The standard error for the estimate of the difference between gender male and gender female. This is not, once again, I want to clarify, the coefficient for gender female. Gender female has no coefficient. It's the reference level. If gender female had a coefficient, throwing a big 100-pointer out here, what would be the coefficient of gender female? Hint, it's the reference. What would be the coefficient of gender female?
0?
You're right. It's nothing. It doesn't do anything to the intercept. It has no coefficient. So there is no coefficient for gender female. it is true that the gender female line has the intercept that is the intercept, but then you'd have to say the line for gender male has the intercept of 65 point yada, 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 because you'd add that on as someone's male. So interpret this right here. I would say two individuals who are otherwise identical, meaning they have the same weight. I'm fine if you just say otherwise identical. Two individuals who are otherwise identical, but one is male, indicator level, and one is female, reference level. The individual who is male is expected to be 5.018 inches taller than the person who is female. And I'll repeat that once again. Two individuals who are otherwise identical, where one individual is male and the other individual is female. The individual who is male is expected to be 5.018 inches taller than the individual who is female. And if you look over here at the graphical representation, you would see here on the black line, we have two people who are identical in the weight if we just scroll up. And if they're identical in the weight, then we would expect the difference right here to just be 5.018. And can I get the AB line on that? AB line, let's go. We want a vertical line equals 150, and there it is. And line width, so there we go. Look at that nice black line right there. And then let's do col equals purple. Cool. So now we can actually see what I'm talking about right here. Is you have two individuals where they're here and they're here. They have the identical weight. Two people who are otherwise identical, but one is male and one is female. The one who is male is expected to be 5.018 inches taller than the one who is female. And that's exactly what we mean. It's easy to see with only two variables, but they are identical in their weight, and the only difference between them is this. And then the only difference would just be this difference, which is the coefficient of the model. It's literally 5. Go ahead.
Did we say on average at the end of that or no?
You could say is expected would mean like a long run thing. Be careful if you notice, and I hope I said this every time, I keep saying is expected or we expect. I hope I never said will be. Will be is a wrong word because if you say they will be this different, and someone could rewind the tape, and I hope I did not say will because I usually count off for that. Our expected is key, and on average goes along with that theme. You could say on average, like on average we expect this. The will, I'm usually a little bit, I don't know, sometimes I'm nice on it, but we don't want to say they will be this different. We want to say that we would expect them to be this different. Does that make sense?
Yeah, that makes sense.
Yeah. Will is just a very strong word, like almost like a cause and effect, like they will differ by this much, but I expect them to differ by this much is different, which is, it's the lines. If these lines are a good summation of reality, then I'd expect someone to be close to the line, and this is the expected difference. So great questions there. So I always love how you can add on little extra stuff to these graphics. It's pretty cool. Next, let's look at this. So we have here a categorical variable. Let's throw in an interaction to make it nice and fun now. Now, hopefully we might see some crisscrossiness in the lines here. And let's call this int right here. It's going to be pretty funny or pretty interesting to see what happens here. I wonder if it will visualize this still the same nice and neat way. Okay, let's give this a shot. Let's make our model int, and let's see what happens. See, enter. Oh, is there no interaction? Oh my gosh, look at that. My model with my categorical, so if you noticed, here, let's view this one. Oh, is it really that crazy? See, that's just that's the value there. The interaction. Oh, did I overwrite this model? Because I shouldn't get the interaction. Okay, good. Here's my original model. Let me take off the AB line. We need it for that one. And then here's my model with the interaction. Oh my God. Okay, why did it not change? Okay, this is a great question right here. Why does the model look virtually identical?
That interaction is just not significant.
Exactly. And when the interaction is not significant, the lines will look very what?
Well, parallel.
Exactly. So this is a completely insignificant interaction. And yeah. So I'm trying to think what we have in here that is very significant. Let's go GPA here. It's a little bit more, that's actually statistically significant. You notice the males actually have a positive slope and the females have a negative slope. So how does GPA impact someone's height? This is nonsense, non-cause and effect stuff. But how does GPA, and probably it's due to some outliers in the data set, these are outliers in the model because they're pretty far away in the bivariate sense, but they're also points with high leverage. Actually pulling the model up. This is a very weird model. The zero GPAs actually are weird. I'd almost toss them out because you can't get into UT with a zero GPA. So I would say someone did a misreporting of the data. If I was using this data set for real analysis, I would toss out the zeros because you can't get into UT if you had a zero in high school. But how does GPA, what relationship does GPA have to height? So key question right there. What relationship does GPA have to height? You always need to start with one thing here because the interaction is actually statistically significant. You need to start with two words. It, what? What relationship does GPA have to height? And you always want to start an interaction with it, starts with a D. It what?
Depends.
It depends. It definitely depends. Because what we see right here is that the coefficient for females, let's look here, female GPA, the coefficient of GPA is actually positive for females. And you see right here, GPA has a positive coefficient until we use gender male, which this would become a 1. And we could try writing this implicit line right here real quick in the next moment. But the coefficient is actually going to be close to what? Just round those numbers nice and neat. The coefficient for gender male GPA, or GPA when someone is a male, the coefficient of GPA would be probably what? Just round it a little bit. I'll start writing out the male line right here. This is male height. So try to think for a moment and be like, what is the coefficient of GPA when somebody is male? Well, what happens when we write this model out here? What does gender male do when somebody is a male? It turns to a what? If somebody is male, gender male turns to? Gender male will turn to a 1. And so all I'm doing right here is putting in, because if gender male becomes a 1, if you remember on the slides, a lot of times I black this out and I put it to a 1. And then here gender male becomes a 1. So what's going to happen to my GPA? It's going to do what? The GPA that was what it previously was will do what now?
Decrease?
Exactly. I didn't want to write that negative and kind of give it away. But the GPA is going to go down by that much. So the GPA was this, but then we have to subtract off this value right here. And now the new GPA is this, or the new coefficient of GPA. And we have here the line for gender male. And you always want to look at your graphic and confirm and be like, okay, this does look to hit at about 72 if I could trace this line up through here. This does look to hit about 63. And this one has a positive coefficient, and this one has a negative. And this one seems more sloped, which, hint, 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 means that it's a stronger relationship. For those doing some of the take-home, the female line has a stronger relationship here. Does that make sense why female has a stronger relationship? Because it's more sloped. It's a little hard to tell in the graphic, but the coefficients give it away. The coefficient of GPA for female is stronger, just a stronger coefficient, stronger slope to the line. So it's a stronger relationship. Does it make sense how I got those equations right there?
Yep.
Cool. So writing the equations is important. Remember, if you ever have a categorical, you can only turn on one. So you can't, if we had 3, 4, 5, however genders, you can't turn on multiple genders. You can only have this person is this or this person is this. However, they are classified by the categorical variables. So it would just be classifications right there.
So if it was a female, for gender male, we would put a 0 there, correct?
Correct, yep. And then when this becomes a 0, then this right here becomes a 0. And if you notice how quickly I wrote the line for gender female, it was just using that information there. Like I didn't have to mess with anything else. Because gender male is a 0 here, and gender male is a 0. 0 times 0 is 0. 0 times anything is 0. 0 times anything is 0 is 0. Does that make sense?
Yeah, that makes sense.
Yeah. So writing the line for female, which is the reference line, is very easy. It's just, you just write it out like that. It's just, intercept and slope. So it's just your usual stuff. So I really like writing reference lines. They're fun and easy. If you notice here, the coefficient of gender male is the difference between these two lines. So this is not the coefficient of the female, the coefficient for females. It's just the intercept for the female line. Like this is the intercept for the male line, but this is the coefficient for gender male, which is the difference between the two lines. As we mentioned previously, the coefficient for gender female would actually be 0 because it has no difference. Because the coefficient for gender male is 9, which is the difference between the two lines. I've had a lot of people ask that question, and I have a lot of people think it's the intercept, which it's not. That's not the coefficient of gender female. There is no coefficient for it. Let's switch topics here, and let's start predicting gender. So let's go over here to gender, and let's predict gender with height. So we're kind of switching the model now. We're just going to do some model predictions, and let's go here. I think the more data camp I do, the more I flood my mind with like multiple commands and like which command am I using? How does that command work? It just confuses you more. Stop learning. Once you've learned enough, don't learn anymore.
Hey, Brian, do you have time for a quick question?
Sure, go ahead and ask. I'm going to take a bite. You get a long question.
Yeah, it's about the take home. Has anybody had an issue with like they can't load in the data frame?
But do you need to load in the data frames?
Yeah, like whenever I go to load in, like for example, like a Q2 or whatever, it can't find that Q2.
Are you inside of R right now?
Yes.
Go ahead and type Q2. Then do $.
Q in the R chunk.
Do you see how I'm looking at right now?
Oh, hold on. Let me swap back to you.
All right.
Yes.
All right. If you're in an R chunk or an R script, or do it down here at the bottom. Do Q2 and then $.
Okay, so Q2 and then $. All right.
Is anything happening?
The only thing that happens whenever I put that in there is it added a plus symbol.
Wait, when you type Q2 and then $. Do I have the make summer final here? But if you have you already ran make sum final? And you have,
yes. Mm-hmm.
When you look over here in your environment, do you see Q2? Like I don't have it in mind.
It's not showing up.
Then go ahead and do this real quick. Go back here, or just do it in the bottom. Go ahead and type make sum final, and when it appears, because I don't have it in my environment right now, go to the bottom, make sum final, and then go ahead and put in your ID again. Make sure it's the exact same ID. Make sure.
Okay.
And go ahead and just hit enter down here. You can just hit enter down there. And this will make the exact same final every time. So just make sure you are using the same like number, or else it could cause big problems. Now look over here in your environment.
Okay.
So now it's in there. You don't need to, and I think a lot of people do this. If you load data, so were you trying something like this right here? A lot of people try that, but when you do this, the data is already in here. So your data should be in there now. So now
it just populated.
I asked Siri a question. Go away, Siri. So now the data is in there, and you do Q2 $, you'll have access. I mean, you don't have to do that. That's just to reach inside of something. Like if I go survey 10 $, I can reach inside of it. Which just
it's good now, because I kept trying to pull it and it kept saying no, and I ran back down to your office, and I think you'd already went to go get something to eat. So I was like, oh gosh.
Oh, you must have got there like right. We left at like 12:56, 57.
Yeah, I got there at like 1:05.
Yeah, I was headed back to here to start the review by then. Yeah, you missed us by like a few minutes, but no worries. We got it figured out. Yeah, like every once in a while I've left like 5 minutes early, and a student will come right at the end, and I'll feel so bad. But yeah, I was like, oh no, you must have. I was thinking, did you come at like 12:59?
No, it's good. And I sent you an email, and normally I just wait, but I have to work at 5:30. So
no. Ask away. I mean, you're in the review, and it's all you. And I don't want you to not be able to do this. So if you close R and you don't save, you can always save your environment here. You can save it to save what you have loaded up. But if you rerun the make summer final, it'll make the same final. So just make sure you keep track of your work. You maybe save your RMDs or whatever you have open. But if you ever need to remake it, you can just remake it by running make sum final and then put in your ID. Just make sure it's the right ID. Because if you get one number off, and if you notice when you run the make summer final, it reports your ID for the first question. It's like your ID was this. Even if you made a mistake, I mean, don't make a mistake. Like, don't use an ID that's not yours. But if you were to make a mistake, you'd want to copy that ID that you put in and probably tell me, Brian, I goofed. I got it off by one number. But don't change it when you put it in the sheet. Does that make sense? I think so. I think we got it.
Yeah.
Okay, so we'll go to the logistic model right here. No worries. I'm just like, no, I'm really afraid that one or more people might have a problem like entering in their data. And then I'm always afraid of that. So you guys are basically just hearing how I make the exam right now and what I think about. We're predicting someone's gender right now. This is just a simple logistic model. Can anyone explain to me the coefficient of height and what height means in this model? Two individuals who differ in their height by 1 inch. The individual who is taller is what? More likely to be male. All we look at right here is the coefficient. And if the coefficient is positive, that means it will increase the probability of the level of interest. So the level of interest is the one that in logistic is last. So we have male and female. Level of interest is male because male is last. So two individuals who differ in their height by 1 inch, the one who is taller is more likely to be male. And we see that over here in the graphic. That is, people who are taller are more likely to be male. Now, we can do one other thing that's key importance right here, is we can take negative B0 over B1. And we could see, let's just double click the numbers. We take this number and we divide by this number right here. So what we get is 68,439. And let's do some AB lines on this. So what we're going to do is we're going to AB line a horizontal. And you know what, I'm going to take this right here because I've got all these nice colors and things in here. And so we got a vertical line we need right here. And then we are going to take also and append onto it. I think that'll run through, which is my goal of it. We're going to append on one last code, and we're going to go horizontal, and we're going to put this at 0.50. And we're going to try to run and see if it works. Oh, it didn't like my last append, so let's append it this way. There we go. So when you look at this right here, this is actually the 50-50 breakpoint at when we would predict somebody to be female or male. People who are taller than 5'8", like 5'8.5", or 5'9", we would predict would be male. Where people who are shorter than that, we would predict would be female. So this is exactly what we got going on right here, is this is the 50-50 breakpoint. That's why I added a line right here and a line right here to show the 68.43 we calculated. And yeah, this is logistic right here. And we can do other stuff. We can add in some interactions. Handedness is the only other categorical one I think in here. We really need more categorical in this data set. So now we're going to get multiple logistic curves. Oh my. So let's go ahead and make a multiple logistic curve here and add in handedness. And let's see what happens. It made it. Good. And let's summary it. I think this one will show. And let's visualize it. Good, it shows. That's not so bad. If you notice, these are not very different, which actually would tell me that handedness really is not significant. And if you notice, I have a partial F test here, and this comes up every time you visualize a model, hint, 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 partial F test, which if I had an interaction, it would actually show me the interaction. Let's throw in an interaction. Interaction is going to allow for it to get mad at that interaction. What did it say? Oh, that's fine. That's just a warning message. Cool. Oh, cool. Oh, yeah, I've seen this model before. I've done this one so many times. There's only two individuals. There's only two individuals who are ambidextrous in this data set. So it comes out looking this way. I think there's only two. But you get this, you know, like there's one female down here, and then there's one male up here. So it actually creates this shape. Maybe there's 3, and that's creating this right here. But due to the lack of ambidextrous individuals, we get that interesting, and that is actually the strongest curve right there. But probably due to the lack of individuals, we look here, the interaction. Is the interaction statistically significant?
No.
Nope. And this is a partial F test being done right here. The partial F is the ANOVA, which we can do with the drop 1 command. So the drop 1 command, if we take our model and we remove out each one, and this is going to be test equals chi-square. I think that's how you spell it. There it is. Thank you for helping me out. It's capital. And if you notice, this is the exact same p-value I just got. So this is doing the partial F, the effects test right here, allowing me to get the p-value for this, and it's not statistically significant. Even though there's such a big change, it's really due to the lack of individuals. Just to confirm, definitely, anytime you get data, you want to be like, why does it look this way? What's going on? I think there are just 2 individuals who have that. Oh no, there's 23. Wow. But it looks like those 23 people, really their heights are very, very standardized. Like there's really, all the ambidextrous females are down here and all the ambidextrous males are over there. And so, yeah, that is rather interesting. Let's just take a look at one thing of it. We're going to run one last command right here. We're going to go sub and go here, subset, classic commands right here. We're going to subset survey 11, and we are going to do handedness equals, and then ambidextrous. And let's just take a look at this, because this is the way it should look if I am correct. And when we do this right here and we do the height, now remember, these are all, look at that. Wow. These are the heights of all the ambidextrous people. If you notice my command down here, I only took ambidextrous people for my subset. And the heights of these people, and look here at 68 inches, what do you notice? That's where we see our what? Our first male. And that's where this curve goes haywire. It goes just straight up. And then if you notice, there's no females. Now, I don't think this is going to be the way for the other data sets. There's going to be males and females interspersed, but there was no male who was shorter than 58 inches who was ambidextrous. And that's why you see this sharp, sharp, sharp slice right there. That's weird. It's weird that there's like no male here and no female there, but that's the way it looks. And that's kind of what I thought had to happen. I thought it was due to little amounts of data, but there's a very strong relationship, but due to the sample size, it does not seem to be statistically significant. So, yep, I thought we'd have less than that. It's just really strong, but not statistically significant. Strongest relationship due to the steepness of the sigmoidal curve. So we could try some interpretation right here. I'll go back to the interpretation. Ay. Okay. So what we see here is that height has a positive coefficient, but the coefficient of height is for which handedness right now? That's the coefficient of height for what? For which handedness?
Is it right?
Ambidextrous. It's ambidextrous because we don't see ambidextrous. So this is the reference level. So if you were to write out the equation, and we'll solve this equation here in a moment, but if you were to write the equation, it would be, let's write right here. I'm down here still. No, I can't do that. This is so weird. I'm like clicking up here. This seems to happen when I do Zoom sometimes. Am height. So this is the height of someone who's ambidextrous equals, and that's, we're predicting probability male. AM gender, there we go. And this is height, and we need the intercept here. And it does this to me all the time, guys. I have no idea why. You hear me clicking it, right? There we go. It stinks because I have to go back and forth between it. And I think that's got it now, actually. That's good. And I'm going to put something else here, logit of this. So this is the logit of it, and this is not solved yet. So what we have going on right here is we can solve this equation. And what's going to be really interesting is I'm betting if I put in 69 or so right here, let's just take this equation, and let's go right about to here. And let's go times 69. Exactly what I thought. And you know what happens at 68? Oh, it's at 60. It's at 67. It does it. And it, sorry, guys. This points to some interesting stuff. If you notice, at 68 inches, the person has a positive value solved. Does that make sense? Do you see that? And do you see the data? Because at 68 inches, we would predict they are what? And you can look at this black line. This person would be predicted to be what at 68 inches?
Male?
Exactly. Because when we think about logistic regression, the way it works is if you get 0, it's a 50-50 split. If what it predicts is positive, then the probability is above 50%. If the probability is below 0, then it's below 50%. I need to drink a little water here. So when I put in 67 inches, it rightly predicts that the person is what? And you can see it right here at 67 inches.
Female.
Female. And it's actually doing this properly. Now, this is not, the probability someone is female is not -14. The probability someone is female is going to be e raised to the -14.1, I think it was, over 1 plus e raised to the -14 over 1. Or I just reset the same thing. E raised to the equation over 1 plus e raised to the equation. And if you notice, this is an extremely small probability. We can always check that if it were to be 0, then we should get the 50-50 probability. And there's the 50-50. And as it goes positive, if the number's positive, we get numbers above 50%. If the number's negative, you get numbers below 50%. And that's why putting in such a negative number gave us basically 0. This number right here is basically 0. Does that make sense? Like when you look at this, you're like, oh, what is the probability if you were right here? It's basically 0. And then if I were to put in 15.03, it's going to return to me basically what? One. Because this is someone who was, how many inches tall were they? 68 inches tall, which is if we trace up right here. So what is this going to return back now? It's going to return back basically 1. Because it's a very, very strong relationship. It basically says, like, you're certain these people are male and you're certain these people are female. Does that make sense? And does it make sense how I'm using the equations right here?
Yeah, that makes sense.
And the biggest thing is the e raised to the equation over 1 plus e raised to the equation. I also did the mathematics to find the 50-50 breakpoint earlier on for the easier example with just the 1 line. So this is some of the math we're using right here and some of the interpretations. We can also look at, and this is a key thing, the confusion matrix. And it will autocorrect that. There we go. And so here we are with the confusion matrix. And this is our second model we created with the handedness. And we can see the naive model gets wrong 313 because it would predict everybody is female. But how many does our model get wrong? You guys can tell me the math if you want, but our model gets wrong how many? Like how many? This is a good take-home question too. How many does our model get wrong?
Is it 264?
Our model gets wrong this. Why does our model get wrong these people here?
Because they're actually male and we predicted female?
Yep, and our model also gets wrong.
Up there.
Yep, and so you would add together those two numbers, which I believe in my head is 88 people. So the misclassification rate of our model, I keep clicking up there and it doesn't do it, is that right there. So that would be the misclassification rate of our model is that compared to the naive misclassification, because the naive uses the majority level, would be this right here. So our model gets wrong 88 out of the 699, and the naive gets wrong 313 out of the 699. So our model does better. We could look at our gender original model. Oh, because I'm not down there. This gets wrong 89. So this one works a little bit worse, but it does not like me today. 89 divided by 699. And so this one works a little bit worse. All I'm doing is adding up the off diagonal, because if you predict someone is female and they're actually male, you've gotten them incorrectly predicted. And you know, that's the main themes of logistic. Are there any additional questions on logistic before we go to model building? Do a little model building with stepwise. think we're good. So let's look at a little model building with stepwise. So let's start with a step function right here. And if we really wanted to predict gender, so we're going to need two models here. Let's predict height. It's going to be a little bit easier. So we need LM. Let's call this naive. And the naive model doesn't have anything in it. So we're going to predict somebody's height, tilde1, comma data equals survey 11, 10. And then we want the full data set or the full model and height tilde dot data equals survey 10. And then we got it. So the first thing you put into your step is you give it the model you're starting with. And then you say scope equals list. And then we say the lower equals naive. And the upper, I don't think it's capitalized, upper equals, and then we say full. And then we do direction equals both. And we get to see all the fun if everything works properly. Cool. Looks like it didn't do that much. This is the model it made for us right here. And once again, it's judging these models based on AIC. Every time it does this process, and a little longer than I thought, it goes so quick. Every time it starts the process, it starts with nothing in the model if I start with the naive. And that's what you see right here, is we start with the naive model, which is where I asked it to start via this command right here. And then it puts in desired weight, because desired weight's actually going to lower the AIC the most. So the next time we see it, it has desired weight in it, and it actually has that AIC. Now it's going to put in what? It'll put in gender, and then next it's going to put in weight, and then next GPA, and then number of body piercings, and then weekly hours video games, and then distance moved. If you notice, I want to point something out. None is the second highest right here, but it's not when you go to the next one. Things can shift around, and finally none hits the top, and then it stops. It's done. And now we've saved the model into here, and we can summary the model, and we get our summary of the model right here. Now, we usually just keep this as is. You can do other things. I mean, there's 10,000 things you can do, but sometimes we just take this model as is. And this model explains 64% of the variation. Basically, if you round up, 63.5. And the R-squared adjusted is also very good because we do not penalize ourselves that much if we look at the inclusion of more variables. It's not that much worse of a model due to the extra variables. And so this is a pretty decent model, and we would hope it's a good descriptive model because we based it on AIC. We could also do the reg subsets. This is a bad idea, guys. Let's see here. And I swear I am clicking here. See, it is not. There we go. I think it doesn't like the blank line or something. Let's call this all. And let's go reg subsets, and let's do the reg subsets and grab our model right here. And it should go model exhaustive right here. Let's try this. Let's see what happens. It might need really be good. Did it that quickly? Wow. Good computer today. See models, and let's look. Okay. So this was the exhaustive way of doing it right here. And you can look at the models it made right here, which we actually got some AICs for these models: gender, weight, desired weight, GPA, number of body piercings, weekly hours, video games, distance moved to school. This might actually be the same model that we got. It looks very similar. And if you notice, the AICs of these two models are virtually identical down to a decimal place we can't see. But yeah, desired 1, 2, 3, 4, 5, 6, 7. Are those the same models? We said sometimes the search procedure can get you the best model. It's quicker, but yeah. And you can, of course, do crazier things. You can include the interactions. So let's include some interactions right here. And I probably shouldn't do that. Was it saying, oh, that's just a graphical error. That's fine. I get that do try catch error a lot. That's just a graphics. Like if I rerun it, it won't give the same error. I think it's because of the window size on the right. But now if we were to summary this model right here, this is a much crazier model that we just got from the, there we go. So this is our model now, which, oh no, this is a bad model. This model has a lot more variables inside of it. And I'm a little bit afraid. I'm not, you guys have no, I really want to do that. I really want to run this. But if you notice how much longer the step command, what should I do? I need a vote from the guys. Should I do this or not?
Yeah, do it.
Yeah, do it.
This is a bet. Okay, so which one's really big? You guys are both like, yeah, do it. Let's find out what happens here. All right, so now it's running. Might have to stop it in a moment. Who knows? But you can tell, and this is the issue, and this is good we bring this up and talk about it while it's doing it. The step didn't take that long, and it probably would have took less time if I didn't have trace true. Trace being on lets you see what's going on, which is good if you kind of want to make sure your computer's not crashing, like we hope it's not now. But the interactions ran like that, but the interactions caused like a lot more models. And I know my computer can do this. I'm hoping I might hit stop here in another 30 seconds or so. But you just really want to find out sometimes. So as it said, exhaustive search will be slow, and it wants you to see that. Must specify really big equals true. I think we got it. I think it's getting close. I'm in tune with my computer. I can feel it finishing up. But this is why we have search procedures. Search procedures are created because this isn't even a big data set. This is not a big data set. This has like 30, 40 variables in it, tops. And so we were able to do it without the interactions. And then with the interactions, I'm getting very close to hitting that stop. And this doesn't even include variable creation or polynomial terms, interaction with the polynomial terms. Everything just balloons out of control. And even the best of computers these days can't handle doing every single possible model for every which way you can think about it. And this here is the epitome of why we have the search procedure. Like, I'm glad we did this because everyone's always like, well, why can't you just always do all possible models? It's like, because you have too many variables. And that's sometimes why we do a search procedure. And then you can do an all possible model with the search procedure, which you might see on your assignments and stuff like that, or on your take home. I'm going to give this one more minute. But this is the idea of building a descriptive model based on AIC. I really want to see it complete, don't you guys? I really want to know. But this is the epitome. I think the fans turned on in my computer. Okay, 10 seconds. Ready? 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Watch, it's gonna do it right when I have it over. It's gonna be like, I got this. I wish it had a complete bar. I wish it would estimate how many permutations it needed to do. Like it just did the mathematical calculation, which is not that hard to do to figure out how many it has to do. And then it gave you a completion bar. I'm stalling so I don't have to hit stop. You have 10 last seconds. This is it. If it doesn't do it, it's done. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Hopefully, can you guys still hear me?
Yeah.
My fan is definitely turned on my computer. I should not have done that. The epitome of why we do not do that. It probably reset. Unable to establish connection with our setting. And now we have learned officially why we do not do that. I don't think, did I lose everything? Untitled 8. Oh, please tell me I did not lose it all. Untitled 11. Boom, we're back. So what did we learn? Don't do that. Okay. So I mean, I'm glad we saw that because that is the reason you don't do that. Let me put here data survey 11 to start because I have to reload in that stuff. So I've got to load in library reg class, and now I have to load in data survey 11 because I crashed my R10. I keep saying 11. I don't know why, but okay, we're good. I'm back where I was at. I don't have any of my models, but we can make what we need. But this is what's going on right here. The reg subsets can use an exhaustive search where the step procedure adds and subtracts things in and out based on AIC. Let's go on and look at a model now. Okay, let's make a predictive model. We're going to predict one of your heights. So let's go ahead, and to make predictive model, we need a train, and we need a holdout. And so now we're going to make train rows. Let's call them TR. Train rows are going to be a sample. And we want to sample from 1 to the number of rows. You can actually just type in here 6. It's really good coding practice to not put numbers where you don't need them, because then you can adjust the code for whatever you want. So I don't know why I just did that. I want to then take 80% of survey, the number of rows in survey. There we go. Okay. So here we go. If you notice, this is 559. I can adjust however that is by this much. So I can change how much percentage I want. And if we are doing this for practice, we want to do a set seed. So I'm going to connect these two onto each other. So that way, if anyone else runs this code, they'll get the exact same thing I'm getting. So here we are with the same exact code. And now all I'm going to do is I'm going to go to survey 10, not 11. And I'm going to go in here. I'm going to take the train rows and put them here. And then I'm going to go here to survey 10, and I'm going to take not the train rows. So if you notice, when my train appears, it has 419, and my holdout has the remaining. So you always want to make sure that your train has the rows you need and your holdout has the rows you need. And if you notice, train rows, there they are 419 randomly selected row numbers. So that's what we got right here. We are good. Code written. Now let's make a model. So to make the best predictive model, I'm going to use the build model command. Let's just store this into BM out, and we'll use the build model here. So using the build model command is very, very, very similar. And let's not use, because the build model is going to do all possible models. So this right now would be a very bad idea. And let's remove that from ever existing. Like I said, we could have done it in the step. And I think this should work. It's going to want a yes input. Many people have gotten stuck on that. And it shouldn't take too long. 3, 2, 1, you're done. There we go. We got it. Cool. We got some nice output to look at here. Oh, no. Hey, guys, yell at me. Yell at me. I was copy pasting code and I did something really stupid. You don't see it? I'll change it. No one saw that. I used my survey 10 data to make my predictive model. The whole reason I made my train subset is because, and you notice it might change. I didn't notice if this changed or not. It does change. It actually, we might have still the same 2-variable model. It's telling me the gender, male, and desired weight, and gendered male and desired weight. But here's the thing. Even with these same two variables right here, I need to then build my model. As in, when I make my linear model right here, I'm going to call this model predictive. When I make this model with those variables, my data must be the trained data. So, and gender male, I did another classic mistake right here, is the indicator, and there we are. So I now have my predictive model, and then I want to see how my predictive model works, which I'm going to look at the generalization error for my predictive model, and we want to test it out on the holdout. And yeah, is this a pretty good model or not a good model? How is this model looking?
Pretty good.
Yeah, and we could do the ratio. It's not biggest over smaller. You have to take these two right here, and you just take the holdout to see if it's bigger than the train. And usually it is. I mean, that's what you expect because it's new data. And it's only 6% or 7% bigger, and that's not that bad. Our typical miss when predicting somebody's height is about 2.8 inches when we predict on new data, which it was 2.6 to start, and it's 2.8 now. That's not that bad. It's a pretty good predictive model. So yeah, I'm liking this model right here. And this is the essence of predictive modeling right here, is to get good predictions. And this model seems to do it. It seems to be a good predictive model. We could look at the other model. Let's go here and take this and just drop it in. And I think gender male is the only one I got to change. Handedness left. And I'm going to include all of handedness, even though it's going to create 2 of them. It's very similar to this model. Let's see how it does. This model actually works better. This model actually works a little bit better. And this is slightly different than the model it suggested because it grouped right and ambidextrous together, making that the reference level, but I slightly changed it. And yeah, so this model worked a little bit better. And it still predicts a little bit worse on the holdout. But once again, I want to make this clear. The way to judge how good a model is how it works on the holdout. But the way our model is selected is how well it works on the what. I've said this a lot in class, I know. The way we select our model is based on how good it does on the
training data?
On the validation. And so the training creates the model. The training creates it. The validation selects the best model, and then the holdout is the test of how it does. So it's like this. I use the cookie example a lot. I go to the grocery store and select the ingredients. I'm basically creating the model there. Then I give it to like one of the students to taste the cookies. They're the validation. Like it's kind of being tested on them, but not really. Like that's not the big test. And then when I give the cookies out to the class, that's the holdout. Like that's how it actually works. So what actually created the model was Brian choosing the ingredients. That's the training right there. It's created from that. I create the cookies, but then we test it on like a small subset. And that's the validation subset, which is actually a k-fold cross-validation process. Do you guys want to hear anything about that? Or what would you, like if you have questions, ask. I know I'm mentioning a lot of theory here right now.
I would love to hear more about the k-fold cross-validation.
I'm trying to think if I could draw like 4 boxes on the screen pretty quickly. Can I annotate on the screen? I don't even see like my Zoom thing. Where's my like annotate more? Where's annotate? I swear it used to have like draw on the screen. But the way the k-fold cross-validation process works is imagine this right here. This is group 1, and don't look at this graphic with the numbers in the thing. I wish I just knew how to draw a square in our studio. It's amazing the simple things you don't know how to do. But imagine this is a box, a box, a box. There'd be 4 boxes here, right? So we break our data up into, we take our training data, like if we had 400, I'll write it out up here. If we had 400 observations, we would randomly put them into groups of 100. Does that make sense right now? We're putting them into random groups of 100. And the first time we run the k-fold cross-validation process, we make our model from this group right here, and then we test it on these 100. Does that make sense?
Yeah, that makes sense.
And then the next time we make the model, we run it on this one right here. Well, excuse me. We take this out, so it's kind of held out from the model, and then we create it from the other ones. And then on the third fold, we create the model from those 3, but not this one. And then on the last fold, we create the model from the first 3, but not this one. So everything has a chance to be what we tested on, and everything is in the model every time but one. And what we do is we then kind of average those models to figure out what the coefficients should be. The coefficients are created from the best models that worked the best on the tested data. So it creates a model that has like what we call internal validation. I think that's the first time I've said it, but it's the way I originally learned it. Like the model's internally valid. It works on itself. Like it can predict itself if you leave portions of it out. It's not going to fall apart due to some points. So the model is internally valid. And so this is the internal validation, but what we have way over here, and I swear I've been clicking, I clicked right here. What we have way over here is another maybe 100 points. They don't need to be all equally sized, but this is never used to make the model. And that is the what data. It's never used to make the model.
The holdout?
Exactly. That's the holdout. The validation is inside of the train. Like this right here is the train. These 400 data points are the training data. That is the train data. The validation just moves through and becomes a validation portion as we make the models that make our overall model. Does that make sense? And once we have a model that's internally valid, we test it out over here. And you're actually seeing the estimated generalization error. If you look over here, I think this was the last ones we ran, we thought, well, let me ask you this. Here, this is great. We have all this all on the screen right now. How well does our model work on the data it was created from? How well does our model work on the data it was created from? What's the RMSE for that? How well does our model work on the data it was created from?
At 2.5.
Exactly. That's the RMSE of the data it was created from. How well do we think the model will work on new data? And you have to look and kind of estimate this by graphic.
2.62.
Yeah, that's exactly what I was thinking, 2.62. And we're taking this, and we were using this model here. We originally did this model, and you notice they're so similar that it's like, well, this one or this one, and they're within one standard deviation of each other. So they're basically identical. This is how we think it will do due to the estimated generalization error, which is the validation. The validation is an estimate of how it'll do. Then how did it actually do on new data?
.7.
Exactly. And if you know what's interesting to me? That's within the one standard deviation, if you think it's right about here-ish or so, and that's within our uncertainty of how well this will work. Because we're like, oh, I think it'll do about 2.62, and then it did 2.76. And someone would say, oh, you were so far off. You said 2.6, it was 2.7. And you're like, well, that's within one uncertainty, because we're like, 2 points. And that's why we could have used this one. And if you notice the output from this one, it was as bad as 2.8, which is actually a little further out than 1 uncertainty, but still. And we usually think it's going to work worse on new data, which I really want to get into the theory of why we don't usually make these higher. I don't know. It does work better every once in a while. Never know. And then over here towards the end of this, what do we see as we add in more variables and the model gets worse?
Overfitting.
I've nailed that down. You guys are like overfitting. We see the naive model up here. The naive model does horrible. It's way up there. It's the naive model with no variables. But yeah, that's kind of the idea of predictive modeling in a nutshell. Next, let's do a little R part right here. So let's make our tree, and let's do R part, and let's go ahead. And you know, we could take this formula. So I'm going to take this formula right here that I got, and I'm going to make a predictive modeling with R part and see how it works. So I just made a tree. Well, we want to use the build tree command, right? Build tree. Cool. Okay. Okay, here we go. The build tree command is like the build model command. I'm trying to think what tree it stores if I do that. Let me visualize this. It's visualize model still, I think, right? Let's find out. And the answer is yes, it works. And this gives me 1, 2, 3, 4, 5, 6, 7. It gives me the 7 split tree, or 6 split tree due to 7. So it's actually giving me, and that is 7, right? I believe it is. Yep. So it's actually giving me this one right here. That's interesting, which I could get this same one due to my own choosing. And why does that happen? I swear I'm clicking up here. Okay. And click right there. I think Zoom does something weird to this. Every time I'm inside of Zoom, it acts funky. And I think I put in one too many zeros. There we go. Okay, let's try this one right here. And I think I have it, and I'll explain why. Cool. And it should give me the same thing. No, what did I do? Oh, it is an extra 0. Yeah. And we should get, yep, we get the same tree. If you notice, this is a 6 split tree, because 6 splits will give you 7 leaves. So we have 1, 2, 3, 4, 5, 6, 7 leaves. And that means we have 6 splits, as in 1, 2, 3, 4, 5, 6 splits, these little divisions right here. And truthfully, the ones we should be looking at are the 3 split and the 7 split. So you guys go ahead and tell me a CP that would be good to get the 3 split tree. So I'm going to go with the simple tree. I want a 3 split tree. What CP? I should enter in 0.0. Oops. Ay, ay, ay. Same. 0.0, and I think it's 1.6. Let's look. You want to go slightly above this, because it's going to put a line right in between here, and it's going to split down to the 3 split tree. So we should get 3 splits, which is 4 leaves. Let's visualize. 4 leaves, 1, 2, 3, 4, 1, 2, 3 splits. And this is a simple tree that predicts someone's height. I mean, think about it. You would just ask someone, how much do you want to weigh? And that's, I mean, think about it. If you just ask someone, how much do you want to weigh? And they're like, oh, I want to weigh, 200 pounds. And you're like, okay, I think you're about 6'1". And they'd say, yeah. And looking at this, you can see desired weight. Do you want to weigh less than 157? No, you go over here. Do you want to weigh less than 176? No, you go over here. Do you want to weigh less than 157? Yes. Do you want to weigh less than 124? Yes. Well, you're probably not that tall. We can take a look at how this model does. Let's look at the generalization error of it. And let's go to tree and see how it does on the holdout. And how's it work? Well, it works, meh. It works and not as good. It works almost as good, but good try at it. Let's try and think of what we do next. I don't know. I don't think I included random forest on the test. I went more theoretical on random forest, and I'm afraid of how long it could take. But the idea of a random forest is we keep creating these trees. And the interesting thing about a random forest is we actually grow the trees to the maximum. I'm wondering what this is going to do. So each tree in the random forest, I should just put CP equals 0. Apparently it's going to have a hard time visualizing this right here. Oh, there it is. So each tree is grown to the maximum, and you get trees that look like this. And then the average of each tree's prediction is taken. But it's important we know how these trees are working, because I haven't even talked about the theory behind these trees yet. In this tree, how is it deciding how to split height? It's deciding how to split height by, and this is going to look even more of a mess right here. It's going inside of, right when it goes to here, it's looking through each of the x variables at each unique level of the x and going between those, and then figuring out what's the best split to reduce the sums of squared errors. So since this is a quantitative variable, it's going to look at the sums of squared error reduction and find the best sums of squared error reduction. But if I were to predict gender, it would do what? It would try to reduce the what of the tree, the what of the leaves.
The AIC?
The impurity. The impurity would be reduced because we want to have the smallest, and let me make this a tree we can actually read again. So right here, when we predict somebody's height, I want to make sure I say it properly. When we predict someone's height, we want to have the closest prediction as possible and have the least error. But if we were to predict somebody's gender, and let's just switch this right here to gender, and I guess we can include height now. Now when we do this, who knows what tree we'll get, we're actually trying to predict, see, it does it by body piercings, which is a pretty good way to predict somebody's gender. It's just be like, how many body piercings do you have? Okay, you have, and just think about this. Why does it do it on only one? It's because there's a lot of guys who have like just one ear pierced or something like that. It's, you know, it's not super uncommon, but if girls get their ears pierced, usually they get 2 pierced. So if you have more than 1 piercing, very likely you're female. If you have 1 or less, because you can't have a half a piercing, and that's why it goes between those. So it looked through all these variables I fed into it, and it did this. We can see if we can make a little bit bigger of a tree. Let's go ahead and put that to that and see what we get. Now it's doing it by desired weight, which makes perfect sense. You'd ask someone their body piercings, and you say, how much do you want to weigh? And which of these leaves 1, 2, 3, or 4 is doing the best? Which of those leaves is doing the best? Sorry if it's a little hard to see there. I think it's actually easier over here. Which of these leaves is doing the best? Leaf 1, 2, 3, or 4? Leaf number 1. Leaf number 1 is doing the best because we want to have impurity. We don't want impurity because if you notice, pretty much everybody in this leaf is female. We actually have 1 male here, or maybe 1. We could find out. Let's find out real quick. 1 divided by 215. And no, we have 2 because that's the percentage. That's the 0.009%. So there's 2 males in that leaf. There's 213 females. That's what that 0.009 means, is that 0.009 of that leaf, or 0.9%, is male. And we would predict everyone there would be female. These are individuals who have more than 2 body piercings, or 2 or more body piercings, and are less than 170 pounds. So, but it makes sense if somebody weighs more, then they are more likely to be male. And we see this in both. We can let's make it a bigger tree again. Let's go, who knows how big this is gonna get. Watch out. What do we get here at this tree? And is it the same? It might be the same. I can't tell if it's running. Let me actually make this the proper way and see what we should be making here. So the build tree is just an investigatory one to look through and kind of see what we get. And there's no more ways to split it. I'll be damned. It actually gets the minimum CP right there, and it breaks. So I'm gonna ask it for more. We were just feeding in certain variables, and so we can actually make it do more. Wow. It really doesn't want to split anymore. It's saying there's nothing it could do to make it split with this CP of 0. So that's the maximum tree you could get. And frankly, the best tree to get is just the one where you ask somebody how many body piercings they have. So that is, yeah, it won't split the tree anymore. So it's like, nope, not going to split. And basically all these models are very similar. If you look at these models here, they're all very, very similar to the one variable model, or the one split model, excuse me. So they're all very, very similar. Let's go to the build tree again. Here we go. So yeah, and actually it's funny that this one goes up. That's so rare to see something like that, like goes up then down again. But yeah, this is our models and this is our uncertainties. Questions about this? Silence.
I'm okay on it.
Cool. And then I guess the last thing we have is time series. Just kind of an overview of time series today. The biggest thing we talked about was using the autoregressive models. And let's see if we can, do we have any good time order data? I wonder if anything comes up with time series. No. Is it salaries? We had the data today. I don't think salaries are. I'm trying to think if we have any good time order data inside of here. Actually, where's my temp data? Let me pull this up. Where's temp data? Temp randomness. Here we go. So there's some time series data. And does this not have everything? Where's my other stuff for the temp data? I'll actually show some time series stuff right here if I can find it. Where is my, looking through like thousands of things that I, we'll give a quick look for this and we'll actually look at a real time series model right here. Where did I put that? Every little bit of code. I write something cool and that I really enjoy and then I forget to save it. There's differential equations. Well, did I never save my temp data thing? That's such a bummer if I didn't save it because it's pretty cool. Let me pull up the temp data and let me see if I can get it to run. Okay, there we go. We've got this right here. Let's pull up. And is it AutoArima? Oh, I need to load in library forecast. I'm going to totally cheat and just show a little bit of this right here. There's library forecast, AutoArima. And can I remember the commands for AutoArima? AutoArima temp data. I'm not going to remember the command for this. That's not it right there. Okay. Oh, look at that. You see stepwise inside of here. Yay, stepwise. AutoArima, and then it wants the series of it, and then we put it to fit. Okay. And then it wants the series of it, and that's what we need right there. So temp data, and there's my temp data right there. It's the CO2 one. There's the CO2 in the atmosphere. There's the mean temperature. I think that is correct. So temp data, $mean. And if you notice, this goes all the way back to, I think, 1888 or so, 1880. So this is the mean global temperature in degree of change from what it was at. And I think, so we talked today about an ARMA model. We talked about autoregressive moving average, and this is autoregressive iterative moving average. So that's a little bit of a different model, but we could actually make one. Let's see here. Is that right? There we go. Cool. Let's see what fit it made. So there we go. And I think I can just do plot. That is not what I want. Is it choosing? Let me see summary. Oh, it's actually doing training and holdout. That's very nice of it. We've got AICs, we got all this coefficients, awesome. And if you notice right here, this is, once again, time series. We're not going that in depth on it tomorrow. There's a lot bigger and better ways of doing stuff. The model it's fitting right here, the AR is the autoregressive, which is a one, it's predicting one period back. I want to make clear what the autoregressive is. You need to know what autoregressive is, which is literally the AR of this model. You do not need to know the I or the MA of it. We didn't go into detail about any of that stuff. But we talked about how this is a model that's actually solved with my model. And you see you get everything. You get RMSE, you get all of this good stuff right here. And I do want it to plot. Plot forecast. How do I do the, trying to remember. For 1 second, everybody. I'm gonna stop sharing for one moment because it's kind of a fun thing to end on. Plot forecast in R. It's funny, I made a really nice, it's just plot forecast? Didn't I just try to type that out? No. Oh, did someone make a function plot forecast? You guys doing all right today?
Yeah, not bad.
Good stuff. Oh, there it is. This Plotarima. Plot. It's funny. It's not showing up my things here. Well,
Hey, I've got a quick question.
go ahead. Go ahead.
Uh,
I didn't hear the question. It kind of cut off. Are you there?
Yeah.
All right.
When I'm running build model,
Yep.
it keeps throwing this error saying that my argument is implying rows that have a different number of rows. I emailed you something too just a minute ago.
Let me pull that up here. Okay, I got the code I needed too. Okay, let me pull up your code. Screen's blanked right now, right, guys? The screen's blanked, is it?
Yeah.
Yeah.
Okay, cool. And was that who was that just talking to me there?
Colby.
Colby. Okay, grab your code, Colby.
I
are
don't
you-
know if I emailed you my code.
Yeah, email me the code real quick. Reply to this email and send me the code. And yeah, just send me the code you have. I knew it. I've got the series reversed, that's why. I had cooler things on this. I think the series is flipped backwards right now. Is it Temp Data 2? Yeah, send me that and then we'll... How did this series get backwards? Temp Data 2. Okay. 2 seconds. And then, have you sent it?
Yeah, I just now did.
Okay. I'm gonna update it real quick and bring it back in. Oh no. Got authentication errors. I'm hoping, it seems like the mails are going through, but I had to change some stuff around today. It says mail has not been retrieved since 1:20, but I got your messages. Oh no. I messed this all up. Okay, I'm gonna have to try to fix this here in a little bit, but I made some mistakes and I was changing some stuff around, but I had to change around some UT stuff. Yeah, send it to me and I'll reply via email to it. So my email's a little bit messed up right now. Let me start screen sharing again and we'll talk. I see the chat. Oh, can you send it in the chat actually?
Yeah, I guess I could.
So, and then, okay, I think everyone got their. So Steven, you asked the question about your data, right? I don't know if Steven's still here. I think he got it fixed up. And then, yeah, just type it in the chat right here and we'll get that fixed up. But you're saying the build model is, oh, let's see. Okay, cool. I got it. Let me see what's going on. Let me bring this. Okay, well, I don't want to display it on the screen. Okay, let me look at this here so that way we don't put it into the. Okay, we got the model being saved from the build model, donation amount, lifetime, yes. Data equals train 2. Does your train 2 actually exist? Like when you look at train 2, is it actually, like go over to your environment and see if you see train 2. Do you actually see train 2? Like, do you?
Yeah.
It has stuff inside of it?
Yeah.
And you're predicting donation amount, SES, and the error it's giving you. See, why would my email work and just break everything? It's technology. It's not liking me this semester. Let me look at. Just send me the full RMD and I'll take a look. Like, send me exactly what you have going on, and I'll run it from the start and I'll see what it is. But everything should run.
You want me to send it in the chat or email it to you?
In an email. Yeah, we'll probably.
Okay.
I figured today's lecture, especially on time series, is probably good enough for everybody. That's why and I wanted to show, of course, start screen sharing again. Let me go to desktop. I was pulling up the plot. I knew it was plot command. It's just the plot, the forecast of the fit. So I just saved it into there. And basically today's lecture really went over everything. My time series model is just backwards right now, which this is actually, here's the most recent temperatures, and here's back to the 1880s. So really what I need to do is I need to just flip the way the order of the rows are. So that's just, I don't know, it should be just an easy command, but my brain is just breaking today on, if I go in here to, yeah, so we'll just talk about this just briefly here. But it's pretty, I don't know, I think, I hear so many people talk about, let's go here to order, watch this, okay. So we're gonna store in here an order thing. Temp data 2 has in it 164 ops, 1,600, yeah. Okay, so this should store into here that, because I can't write today. Okay, good. Now I have in here another, an order variable. So now what we're gonna do is we're gonna do temp data, and then we're gonna order it. Let's do temp data ordered, and we're gonna store into it order and temp data. Should be easier with dplyr. Let me try that. Range. I don't have dplyr on. Okay. And then let's do a range temp data, and let's pipe it into it, and then let's arrange, and then let's arrange it by order, did I call it? Order, and it doesn't like that, of course. Is it order? There's order by, no. Ay. My brain is not working today, guys. I just can't even think of, let me type in dplyr. Well, I want to make my time series data and I just can't today. There's a lot of fun and interesting functions that we need, but my brain is just not working today. I feel like I'm going to cut this last part of the review out. I'm going to cut it before I upload it. Brian fumbles with dplyr. I swear it's a range. Is it order? Let me check and cheat and find that one command. What are you guys thinking or have questions on?
Actually,
I'm doing the take home. I'm just stuck because that error keeps getting thrown.
Yeah, I'll take a look at that and I'll see what's going on with that one thing going on.
I have a question
Go ahead.
on. So in assignment 11, the first question was, in total there are 4 quantitative predictors, 3 categorical predictors with 2 levels, and 1 categorical variable with 7 levels. If we run the all possible procedure without interactions, how many models will be generated? What is there's an equation we use for that, correct?
Yep. And so the equation, let me start screen sharing on that again. The equation for that, when you look at how many variables there are, every quantitative model will introduce 1. So if you have 5 quantitative variables, it'll introduce 1. If you have a 6 level, it'll introduce 5. And I think it said there are like 2 3 levels or 3 2 levels. So it's basically like this. If you have like, if you have something like height, that'll input 1 variable into the model. Does that make sense? Or 1 coefficient.
Yeah, that makes sense.
If you have gender, gender has male and female. So gender would introduce 1. But if you have something like day of the week, if you have day of the week, that would actually introduce how many coefficients into the model?
7?
6.
Yeah.
Because it would not introduce the reference level. So if you have a 7-level categorical variable, that'll do 6. So at this point, to look at how many total models I would create, I would simply do to the 2 raised to the 8th. And I don't ever really use the interaction one because it's almost superfluous, because the interaction one explodes so quickly that you just have endless models with interactions. It's a more complicated one for interactions, but just 2 raised to the whatever power, however many they are. Now, there are only 3 variables, but you have a quantitative variable. So this is just quantitative. And this variable right here is 2-level categorical. and this right here is 7-level categorical. So categoricals always introduce 1 minus how many ever they have. And that is what is going on.
Awesome. Thank you.
You're welcome. I am beside myself that I can't remember a simple command to get this to do its thing. I swear it's a range. So your range is a dplyr command. Yeah, it's gonna, and then the temp data, it's temp data 2. There's the order. Did I just type in the wrong thing? There it goes. That's why, I swear that's why I typed earlier. And then, okay, is this right? Nope, I want to send equals, so to send. I must add one typo. I might have done the wrong, that's why I have too much data set open. Okay, so that's what I want. I wanted to descend the order, and then I want to take this, and I want to store this into new temp. And so that runs right there. Man, sometimes you just got to walk away from it for half a second and then come back to it, and then it just works. And here we go. Cool. So this is the time series model for the weather we're seeing. And if you notice, we do have an upward trend a little bit, but especially due to this recent, I think it's like 2014, 2015. I don't know. It's interesting. It's just, this is where the debate begins, where people start yelling. But if we were to limit this view right here on the data set, you'll notice that there's not, let's look at the most recent years. So let's go here to the plot, and let's go to xlim equals concatenate 1400 through 1644. Cool. Okay, so these are the most recent year, or the most recent data in our time series forecast for the temperature. And yeah, I have some different models that say different, but let's go back a little more period. I don't know. This is where everyone starts the debate, and we look at the series and we try to figure out what's going on. But yeah. But the biggest thing, especially from today, is understanding what an autoregressive model is. We can pull a Durbin-Watson test here. It's not going to let me see the Durbin-Watson today. So we can pull a Durbin-Watson test. What is the command for the Durbin-Watson? Brain's just lost on it. Stop share. What else are you guys thinking? DW test, of course. DW test. Wait, it's not programmed in. DW test. Durbin-Watson.
So for descriptive models, we use the AIC, and then predictive, we use the RMSE when judging them.
Well, you can use the RMSE for quantitative models, but for categorical models, you'll be using misclassification matrix. Because for categorical models, you're seeing if you predict stuff properly into the group that it's a part of. Does that make sense?
Yeah, that makes sense.
Yeah. So in descriptive modeling, it's just AIC, how close is our model to the truth. But in predictive modeling, we either want to use the RMSE or we want to use the misclassification matrix.
Depending on if it's quantitative or categorical.
Exactly.
Gotcha. Thank you.
Let's see. If you guys have questions, feel free to ask them. I'm just getting some code going in here in the background. Exactly, that's where it's at. Okay. Now it'll do. I'm making, here, I'll put my screen back on. I'm making some models over here right now. I think Jessica just joined in. How long have you been in the review, Jessica? we're at the end of it right now. We're winding down with some time series. So let me make the linear model right here. And let's do temp data. I'm going to do new temp data. Okay. Let's predict the mean right here. So we're just looking at a little bit of time series right now. And we're predicting the mean of the temperature change. And we're going to do this via order, which is just a period order. It's just the first period, second period, third period. It's monthly data of time ordered temperature data. And then we've got temperature or data equals new temp. And this should make our model right here. And we've got our model, and we've got the Durbin-Watson test, and it runs. And we actually don't see any auto-regressive. I'm going to go back to a 12-period lag on it. Oh, that we do see. What am I saying? Brain is just breaking today. We see insane. My gosh, look at that. Usually don't see all zeros in that, which just tells you that temperature is highly correlated to a ridiculous degree between the periods. And so we didn't have any really good data today in class for time series. But this idea right here that temperature is time ordered data, and that's why I pulled this up. Knowing yesterday's temperature is very indicative of today's temperature or what it'll be tomorrow. And even knowing 2 days ago what it was, or in this period 2 months ago, is very, very, very. And we're just seeing insane autocorrelation here. I've never even done anything this crazy, but let's see what happens. It might not even like it. It might toss it back at me. But yeah, it's, and once again, this shows that we really need to make a complex model right here to actually figure out what's going on, and all the different models you can make, and you have to fight over it to say who has the best model. And yeah, any other questions before I finish up here? I'm just kind of doing a little time series craziness right here. So let me take and do a order equals concatenate. I'm gonna do a 1, 0. This is the model we did today. Hopefully I can get this to fit. So this is an ARIMA model. And let's look at the mean right here. And there's our model right there. And it's giving the estimates for it. I'm just making a simple ARIMA model. And let's look at this right here. And let's go in and plot my forecast from my model right here from the fit. And we can get the reforecast of it. Oh my. This is why you got to be very careful. We're just throwing around random things right now. We're not really judging the AICs of the model. And we really need to take a look at what's going on in the background right here in the AICs, because if you make a wrong model, things just go haywire. You have no idea like what you're actually predicting. And so which of these models are the truth? How would we judge which of these models that I'm just tossing around right here is actually the truth? How would we know? Any ideas? Should be on here somewhere. It's so much silence. I'm not used to silence. What we would do is we would judge the AIC. We would take a look at the AICs of the model to figure out which of them is closest to the truth. And it's interesting, we had a model that went downward right here. So I want to see the AIC of that model. It's actually not as low as the previous model. So this model here that's actually going downward is further from the truth. So it's not like, oh, I like this model better. You need to find the model that's the closest to the truth. And there's lots of ways to do this, which we'll get into in 474 with like the expand grid idea. And it just kind of, wow, that went haywire. And did we get the summary of it? So that's even further away from the truth. So you really have to watch out, because you can make horrible, horrible things. I'm just kind of having fun just kind of making nonsense right here. But yeah, you have to figure out what your model is, how close it is to the truth, and then justify your model and show it makes accurate predictions. But I think that's basically got it. We kind of went on for like 2 hours and went a little haywire at the end. Any other last questions?
I got nothing else.
Cool, cool, cool. Well, I might cut off the time series part because I kind of just rambled through. Do you guys think I should cut it? I don't know. I just kind of rambled about some time series for the last 20 minutes. But it really is its own course for a reason. There's no simple like, oh, I'm going to do a time series model and get it done. It's a very large and intensive course. But I think that's got it, and I'll let you guys go, and I'll probably chop off the last few minutes here, and yeah.
Awesome. Thanks, Brian.
You're welcome, guys. If you have any questions, email me. I'm going to fix that email thing, but I'll talk to you guys later.
All right, cool. Thanks.
See you guys.